Hey, good morning, everybody, or afternoon, depending where you are, and welcome to this 1-hour webinar on concurrent programming in .NET, presented by Wintellect. So here at Wintellect, in addition to doing webinars like this, we also offer lots of options for you to be able to write better software. So in addition to online training where you can do on-demand training on your own pace, we also do instructor-led training at your site, where you can do more in-depth forms of training, 3, 4, 5 days, and in consulting services as well. So if you like what you see today and you want to get sort of more into it and cover it in more depth, please let us know, and we can definitely take care of that. All right. As far as me, my name is Jason Bell. First started programming on something that looks like this, TI-99 back in 1982 or so, and been kind of along the ride since then. Got involved with Microsoft around 1998 or 99 when I was a member of the U.S. Air Force working on stuff at the Pentagon for the Communication Center. And so during that time, did a few books for Rox Press on different Microsoft development, both Windows and web, and some stuff for MSDN Magazine on internationalization and making applications that can adapt to different cultures and languages and things like that. And mostly now I spend my time going around doing training on .NET, C#, design patterns, web security, ASP.NET Core now, and then even a little bit of Xamarin. So, yeah. Before we get into what we're going to cover today, I do want to mention a URL here on the GitHub. I will also put this in the chat for everybody as well, just so that you can take a note of it a little easier. But at that location, this is where all of the source code and things are for our webinars. So this one is not up here right now, but at the end of the training, a little bit after, all the code that I showed today and demoed today will be available here. It will show up as like 2017, November 2nd, concurrent programming in .NET. We've got about 5 different demo projects that I'll be showing code from, and so all that code will be available to you to be able to download, and it'll be there. Also, there will be a way that you can watch a video, a replay of this. It is being recorded, and we'll talk about that at the very end. Okay. So what are we going to talk about today? Well, it's called Concurrent Programming in .NET, and so one note I will say before we get started here, we will have some time at the end for just Q&A and questions and things, but what you can do, because we have a large group of folks on here, a couple hundred, you can feel free to sort of ask questions in the questions box in the GoToWebinar there, and as we go along, and then I may wait till the very end to answer them, but you don't have to wait till the end to start asking them. And I noticed there's already a question here. It says, is this webinar going to be available for replay? And yes, and I'll mention that again at the very end for that. So if you want to ask more questions in there, go ahead, and then at the end I'll scroll through them and see how many we can get to. Okay. So what are we going to talk about today? Well, first of all, one of the things I notice is when I go around and we do training on concurrency in .NET, that we do find a lot of folks have very common points of confusion or just misunderstanding. And so our primary objective today in the hour that we have is to really sort of focus in on sort of those areas. So I get questions from people like, hey, I'm doing ASP.NET Core development now, and I see that in controllers, people are using the async keyword on some of their controller actions. And I'm not sure, you know, am I supposed to be doing that? Am I always supposed to be doing that? Is it only sometimes? You know, when would I and when would I not? What benefits do I get from it? You know, things like that. And also some of the new things in C#, like the async and await keywords. Just in general, sort of how those work, and you know, people say, well, I'm trying to use async, but I'm not doing await. It's giving me some sort of error. Or I'm trying to await on something, but it's not in an async, and I'm getting some sort of error in that case. And so what happens is people usually go out on the web and they try to find some example projects where this stuff is used. And what you tend to find is either the examples are too simple, you know, it's a console app that does a thread.sleep in a task, or they get a little bit too complicated because there's so many other things going on that you sort of lose sight of how things work and, you know, what benefit you're really getting. And so in this time that we have here in this webinar, what we're really going to shoot for is to try to build an example application that's a little more real world, that we can use some of these things that we're going to talk about. So what we're going to try to do is have an ASP.NET Core application that needs to get currency rates. And so currency rates are available out on the web. You can get them via some web services that are out there, but some web services cost money, some of them are free. The ones that cost money typically have, more up-to-date data. It's only a couple minutes old or even a few seconds old, but they end up costing a lot of money. So other ones are free, but the problem with free web services, they tend to be sort of unreliable, maybe a little bit slow or down. And so in our web application, we'd like to make a call to multiple free web services to get these currency rates simultaneously, right? And then whichever one comes back first, we'll take those results. And that way, if we have 5 or 6 different free web services, we could try them all at the same time, and then whichever one comes back, that's the one we'll use, which is better, obviously, than trying one. If that doesn't work, try the next one. If that doesn't work, try the next one, because, it'll always be the last one, and that sort of thing. And so that'll also force us to deal with things like cancellation. We'd like to cancel the others once we have one that came back, and also error handling. So what happens if we can't reach one of them? We get a 404 or what have you. So that's the sort of example application that we're going to work toward, right? It's being able to call these web services in parallel, deal with cancellation, deal with error handling, and then go with the first one back that wins. And we'll see if we can do that in less than an hour, right? Okay, so we got a few things to talk about just foundationally when we're doing concurrency in .NET. I want to make sure everybody's on the same page here with terms when we go to do this. So the first one is this idea of concurrency versus parallelism. I see folks very often, they'll use these terms interchangeably. Concurrent, parallel, multi-threaded, and so on. But really when we talk about this, if two operations are concurrent, it just means that they're in the progress at the same time. They haven't completed yet. So maybe one's halfway done, the other's 3/4 of the way done, but they're in progress. If they're actually executing at the same time, then they're in parallel, right? And so depending on the kind of work we're doing, one may be more applicable than the other. So if operations are running in parallel, they're concurrent. But if just because things are concurrent doesn't mean they're parallel, right? If we're on like a single processor machine, the system obviously has to switch between tasks. So it may do a little bit of work on one task and then a little bit of work on another task and switch back and forth and so forth. So those are concurrent, and that allows some great benefits for us as application developers, but not necessarily running in parallel, right? And then of course threads are the mechanism we use to make this happen, right? So concurrency is great because the classic example is we've got a GUI application, say Windows Forms or WPF, and we want to keep our UI responsive. And so we've got one thread that's running our UI, and then we do other work on another thread, so we can keep that UI thread responding to events, so they can click the cancel button or do other things, right? So it's not doing things faster so much, it's just being able to keep it responsive, right? Now in the case of a web application, which is what we're going to end up building, concurrency can really help us in terms of scalability. So with ASP.NET, say we build an ASP.NET app, we deploy to IIS on Windows. By default, the setup is that we're going to have one process per application, but then one thread per request. So if we've got 1,000 requests that we're handling, we've got a thread for each one of those requests, so they can all run concurrently. Now, depending on what machine we're running on, if we have 8 processors or 16 or 32 or whatever, we'll determine how many can actually be running in parallel. But that's how we're going to get that scalability. So in our application, what we'd like to do when we start doing the currency stuff is we'd like to make sure that we can either keep our application scalable or maybe even increase the scalability by making sure that we're not wasting threads. We don't want threads basically just sitting around waiting for something to finish, right? When it comes to actually running things in parallel, that's where we can take a problem and to break it up into pieces so we can actually do it faster, right? And we'll talk more about this in a second, but if I've got 8 processors, I'd like to be able to spread the work across all 8 processors and then maybe even, like, in effect, load balance across those processors so I can do the work in the minimum time I can with the hardware that I have available, right? And that's where parallelism would come into it. But for us in web applications, we tend to be concerned more often with operations where we need to do some waiting, like some web service calls or disk access, and not so much needing to perform some really complex operation, which is going to max out our CPUs. Okay, but they can both be appropriate at times. Just 1 second here. Okay. Cool. So threads are a mechanism in .NET, and threading has been around since .NET 1. And that's the construct that we can use to encapsulate a unit of work, right? Something that needs to be done. And we'll leave it up to the system to sort of schedule those threads for execution, right? And this is a topic that we could spend a lot of time on, but usually as a .NET developer, we want to stay out of this, right? In that we want to define what work we want done. We want to define that we want it done in the background, for example, but we want to let the system handle all the complexities of scheduling that stuff. Because there are some complexities involved with the scheduler making sure, for example, that if I have a low priority task and there's a bunch of other high priority tasks, that low priority task is going to get a chance to run. And so the system can do things like temporarily boost the priority of that task to make sure it gets some time to run, right? And so we really don't want to usually be involved in that. However, just to see it, here I am over in Visual Studio, and so I've got a little console application here. And this is your classic example of actually using a thread by hand, right? So I've got my main method here. I go ahead and create a thread, give it some function to run, start the thread, and then we'll print something out, and then print something else out. And so you notice I have this join command in here, and so I do have the ability here just to create the thread, start it off running, right? So you can think of it this way, right? When your .NET application starts up, you have a process, which is really just an area of memory, and then you have one main thread. And that main thread is assigned to run the entry point of your application, which is the main method. Sure, so it's running. During that process, I can choose to create my own secondary thread and then start it off running. And so this do work method that I pass to it sort of becomes the main method of that other thread, right? So it starts off running, okay? And so I could run this, and we'll see that it'll start running the main thread, and then it will start off the secondary thread, and then the main thread continues running. But the point here is, once I start that secondary thread, the main thread keeps on going, right? And so I have my second thread doing some long-running work here. It's like 5 seconds or something. So we see that the other thread, and then the main thread prints something, and the main thread again, and then the other thread jumps in here. So in other words, the main thread was allowed to finish, the main method was allowed to complete before my background work finished. Okay. Now, if I was to do something like, let's take this thread, and when we create a thread like this manually, it turns out that it's actually a foreground thread. And in foreground threads in .NET prevent a process from exiting, right? As long as there's a foreground thread running. If I choose to make this sort of a background thread, okay, and then I run this application, the process will actually be allowed to exit before the other thread finishes, right? So that's something that we have to think about or be aware of when we start getting into our web applications and things like that. When we use a thread pool thread, which we'll talk about a little bit later, thread pool threads are background threads, right? And if we create a thread by hand, by default, those are foreground threads. So what I'm trying to get at here is we don't want to be down at this low level of us creating threads manually by hand. However, sometimes you might have a reason to. And some of those reasons include, I want a thread that's going to be a foreground thread that's going to prevent my process from exiting. Or I've got a thread and I want to be able to change the priority of that thread. Well, if I'm creating the thread by hand, I can do those sorts of things. I can change its priority. I can make it a foreground thread. I have full control. But I'm also missing a lot of features that I'd really like to have. Like, how do I get back results from when the thread is finished? Some sort of callback or something. How do I tell the thread that I want to cancel it doing whatever it's currently doing? How do I handle errors when they occur? What if I want to update the UI of my application from that background thread? Things just start getting really, really difficult. So even though I have control when I create my own thread, it's going to lead to a lot of extra work that I'm going to have to do just for doing little simple things like handling an exception or getting back the results. Those are all things we can do, but I don't want to have to be doing that, right? So if we, in my slides, all right, so threads are also expensive to create and consume memory. So we don't want to really be creating more threads than we absolutely need to. So in .NET, you may have heard of this if you've done .NET programming for a while. We have the thread pool. And so instead of creating our own thread by hand, we can basically ask the thread pool for a thread that already exists and just use that thread to execute our code. It's going to be more efficient in that case, right? We'll avoid the overhead of creating the thread. However, thread pool threads are background threads. We can't really mess with their priority. We have a little bit less control, but it is going to be more efficient. So for example, in .NET, we're not going to do it, but we could do something like threadpool.queueUserWorkItem. Give it a function, and then it can run that function on a thread pool thread for me. Okay, but I'm still going to end up with issues of how do I deal with what comes back, how do I handle exceptions, those sorts of things. So for us, before we start thinking about should I use a thread pool thread, should I use a manual dedicated thread, should I use some of the new task stuff that we're going to talk about? Well, it kind of depends on the work you're doing, right? So if we have a CPU-bound task, like I was talking about a little earlier, these are things that can be completed in less time if we have more resources, right? So we're doing some complex calculations, some in-memory processing on some objects or something, where you're like, man, if I had more processors, I could break this up, you know, my 1,000 items across my 4 processors, and then I could get it done faster, right? That's a CPU-bound operation, right? How quickly it gets done just depends on how much resources you can throw at it, right? And so we have some great stuff in .NET for doing stuff in parallel with the task parallel library. Things like parallel.forEach and parallel.for and parallel.invoke and parallel link. So a version of link that we can have link do its evaluation of our objects in parallel. But a lot of times what you end up doing in your application, especially in web applications, are things that are more I/O bound, right? And how fast these get done doesn't really depend on how many resources we have, but we're waiting on something. We're waiting on the web service to return something back to us. We're waiting on the accessing a file on the disk. These are things that have high latency, right? And we just need to wait more efficiently. We don't want to be using up a thread that's just sitting there spinning, waiting for the results to come back. Because if we've got something like an ASP.NET web application and we want to handle thousands, tens of thousands, or hundreds of thousands of requests, I don't want to be grabbing threads from the pool, but then having that thread spend 90% of its time just sitting there waiting for results to come back from the web service. That's totally a waste, and that's going to hurt the scalability of my web application, right? So this is where this comes up more often and where we can really get some good benefits, okay? So how we're going to accomplish that and really do it properly is in our ASP.NET web app. We want to make sure that we're using some of the mechanisms that are provided by the operating system to wait more efficiently. Okay. In other words, we don't want to have a thread, like I said, just sitting there spinning, burning CPU time, just checking to see if the data's come back yet, right? What we'd like to have happen is the request comes into our web application, we get a thread from the pool, it starts processing the incoming request, it gets to a point where it has to wait on something, like a web service or file I/O. Okay, so let that allow us to release that thread. I want that thread to go back into the pool so it can handle other incoming requests while this file I/O or web service, we're waiting for something to come back, right? Now, once that result does come back, then we want to go back to the pool and get a thread so that we can generate the response and return it to the user. But the idea is if I've got 100 requests that I'm dealing with, and they're all going to do call some web service or something, okay? If all 100 of those requests are currently waiting for the data to come back from the web service, I want those 100 threads to be available to be handle 100 other requests. And then as the data is coming back, then we'll grab threads as needed to deal with that data that's coming back, right? And that can really help with the scalability of our application. And that's what we're going to do. We're going to see how we're going to do that with our ASP.NET Core application. Okay, so avoid monopolizing a thread, just waiting for something to finish, right? And the good news is, when we talk about tasks in .NET, or the task parallel library, tasks are built on top of the .NET thread pool, and will allow us to use some of these operating system mechanisms, like I/O completion ports and signaling of kernel objects, transparently for us, so we don't have to get into those sort of details, okay? Which is really nice. So a task in .NET is really just a schedulable unit of work, okay? It's some piece of work that we want to perform, typically on a separate thread, but we're going to let the system handle the scheduling of that work, okay, for us, okay? So it'll be similar in that when we go to create a task, we'll give it some delegate, right, some function to run for us, similar to when we created a thread by hand. But tasks are going to provide us many, many more features to get those things we really need, like cancellation and error handling and what have you. Okay? All right, so let's create a task in .NET. And again, some of you may have done this before, right? We're going to create a task, we're going to pass it some sort of function to run, and then we can start that. Or, you know, there's even a way we can use a factory, as we see on the slide here, to kind of do it all at once, to basically create it and start it in one go. So what I'm going to do is, let me go over here and look at another sample. And again, all this source code will be available for you. I'm going to look at demo 2. And now we're going to start doing this currency web service. Well, not quite yet. We'll get there in a second. Okay. This first one is just a very simple task. Okay, so we've got a task here. We create a task object. We need system threading tasks. Tell it we're going to run the do work method, start up our task, and then, you know, write something out here. So just like with threads, when you create a task and you tell it to start, the system will handle the scheduling and execution of that. So usually what that'll mean is it'll grab a thread from the pool and then execute that work using the thread pool thread. Okay, and so if I was to run this, for example, you can see hello from main thread, hello from task. So in other words, you can see that I start the task, but I'm actually getting the message from the main thread first, and then I'm getting the message from the task. So again, it's just showing that the task has been started, it's running, but then the code here in main is allowed to continue executing. Okay, and that's something we especially need to think about in a web application, because if a request comes into my web application and I start processing that request, I trigger off some work in the background. Well, that controller action, for example, is going to keep on running. And so when that background work finishes, somebody has to be listening, right? I can't let the controller action finish and return a response to the user, and then my background work finishes, because I've already sent the response back to the user. And so that's something we're going to have to sort of work with, but that's tasks going to actually make that pretty easy for us. Okay? Okay, now, one thing about tasks, so we already said that the scheduler is going to work on scheduling those for us, okay, and there are different scheduler implementations, and you can sort of control how the scheduler runs your tasks. Again, sometimes just the default implementation will work great, but you do have a way to sort of control what the scheduler does with your tasks. So, for example, when I go to create my task, I can specify some task creation options, right? And so as part of my task creation options, I could tell it something like, this is a long-running task, okay? And so that's sort of a hint to the scheduler. So then when the scheduler goes to run this task, it says, well, you've told me this is going to be something that's really, really long-running. It would probably make more sense to create a dedicated thread and take the overhead of that, so then I can use that to run this long-running task versus a thread pool thread, right? Because if it's using a dedicated thread, then it leaves all those thread pool threads open for doing other things, like handling other incoming requests and, you know, what have you. This won't necessarily force it to, but it's telling the system, hey, you know, this is long running, you might want to do something different, right? Now, what's long running? If it's more than 3 seconds or 10 seconds, or there's no real number on that. It's just obviously, if I'm doing something like call a web service or read a file, that's not considered long running. If on the other hand, I'm going to fire up a task that, I don't know, is going to monitor a folder to listen for when files are dropped into that folder and then process them, and it's going to be running for hours, right, looking for these files to show up, well, then that's obviously more like long running. Okay. The other thing is when I start the task, I have the ability to give it a task scheduler, right? So which task scheduler do I want this thing to use? And so I can just use the default one, or maybe I can give it this. There's a method here called this from current synchronization context. If I'm in a GUI application and I spawn off some work on a background task, now I want that background task to be able to update the UI. I won't be able to do it from that background task because there's issues that can result there by updating the UI from another thread. And so what this will allow me to do is in that background task, I could schedule another task which will run on the main UI thread to update the UI, right? So point here is we've got options. You know, we're using a higher level construct, we're using tasks, and it can do a lot of things for us, but we also still have some ability to control exactly what it does and how it does it, right? And so we'll see some of that here in just a minute. Now, let's start attacking some of these. So how do we pass data to a task? So I just had it run a function, but what if I want to pass some data to that function? Well, one thing I could do is I could say, well, let's go ahead and create our task, and instead of giving it a function that just returns, that just takes nothing, we'll have it be a function that takes some object. And so then when we start the task, or when we create the task, we can tell it, here's the function to run, and then here's the parameter I'd like you to pass to it. Right? It could be anything. It could be a dictionary or some object, whatever it happens to be. So this is one way that we can sort of pass data to a task without introducing sort of shared state by just having the task access some variable that it can see, right? Now, in the slide here, it says data can also be passed implicitly using anonymous delegate rules. And this is another one of those points where people get a little bit tripped up if they don't understand what's happening. And so I've got a little example back here in the demo, and this is the code that's commented out. And so I just wanted to show this, which is instead of just running one function, what I'm going to do is I create a list of functions. And then what I do is add some functions to that list. So you can see right here I'm adding this, this function here, which I just have defined as a lambda. So it's going to take the value of variable, which is this int here, multiply it by 2 and return it. But I'm adding this function to this list, 5 times. Okay. And then what I do is I loop through all these things and I invoke it. So we're not using a task here. All I'm doing is I'm basically just creating a list of functions, and then I am looping through and invoking each one of those functions. And the question is, what am I going to see when I invoke each one of these functions? I've got my variable here, and so what I do is I multiply it by 2, and then I increment it, and then I add another function to the list, and then I increment it, and then I add another function to the list, and I increment it. And so when we run this, come on. We're building. Oop, what happened there? I already got something going. All right. Ten. So the point here is I'm getting at is when you capture these values, it's going to capture them by reference. So in other words, when I go to invoke all these functions, it's based on the value that the variable is now, right? What it ends up being, right? Versus what it was when I defined the function. So when I added this lambda expression, this function, and I said, yeah, it needs to take whatever variable is and multiply it by 2. And I add the next one. It's going to take whatever variable is and add it by 2. But again, when I run the functions later, each one of them sees variable as the way it is now when I'm invoking them, right? Versus it's not, when I add it to the list, it's not adding 0 times 2, 1 times 2, 3 times 2, 4 times 2, okay? And so the lambda is sort of capturing that thing by reference so that if it's changed, right? When I go to invoke them later, that's the value it's going to be. Okay, so just wanted to show this little example because sometimes when people are doing things like this with tasks and they're passing lambdas to what they want their task to run, you have to think about how these variables are going to be captured within that lambda and what will actually happen when they run, right? So just something to sort of keep in mind. But when the slide just says can be passed implicitly using anonymous delegate rules, when it says these anonymous delegate rules, that's what it's talking about, is how those values are actually captured and what will be there when the function actually runs. Okay, so just something to kind of think about. Now, what about returning stuff back from a task? Well, when we create a task, we can have that task be defined using the generic version. So it's a task of int. In other words, it's a task that's going to return some int to me. So I can start the task running, and then at some point later, I can ask for the result of the task. Okay, now, if the task is finished, then I'll get the result, whatever the integer is. If the task is not finished, when I ask for the result of the task, that's going to block that thread, right, until the task is finished and I can get the result. So this is like a thread join. It's actually going to block this thread until the result is ready so that it can give it to me. I can print it out or whatever. This can still be beneficial because if I've got other work like here, right, in between where I start this and when I ask for result, well, then this work can obviously be done. Start the task, do all this extra work, and then when I get to here, I think, well, the task will probably be finished. But if it isn't finished, then just wait, make sure it is finished. Okay, so by getting the result. Now, one question comes up here, which is what happens if while that task was running on this other thread, it threw an exception, right? It blew it up. Well, one of the nice things about tasks is when you actually, when the exception happens, nothing is going to really affect your code at that moment. It sort of gets captured and held onto. And then when you ask for result, it will then throw the exception here, right? So in other words, it'll throw the exception in the main thread at the time that I ask for the result. Okay, so it's easy for me to put a try catch around this so I can catch any exceptions that occurred during the execution of that task. Okay, if I never ask for a result, no big deal, I never get it. Okay, but as soon as I go to actually get what the result was, then it'll throw the exception at me, which is really nice because marshalling exceptions from background threads to your parent thread sometimes can just be a pain. So tasks makes that much easier. All right, so another cool feature of tasks is we have some API methods available to us of how we can sort of use tasks in interesting ways. So if we have a collection of tasks, we can then say that we want to wait until they're all finished, or maybe wait until just one of them is finished. And we can even pass a timeout for how long to wait. Now, this sounds very interesting. This is something we could use for our currency problem, right? So I could create a task, I could start it running, and then I could just wait on it. So in other words, block and sit here until it's finished. Or if I've got two tasks, I could say that I want to wait until they're all finished, right? I could call wait all, pass it a collection of tasks, and then I could even give it a timeout for how long I want to wait or how long, not to wait. And so that can be really handy. So let's take a look at an example of that. So I'm going to jump back over here to Visual Studio, and I'm going to open another demo, which we have, which is demo number 3. And now we start trying to do the web service problem. So what I've done in this project is I just have a interface defined for what one of these currency service things looks like. I need to be able to pass it a currency code, euro or US dollars or whatever, and then it'll give me the rate back as a double. Okay? So I'm converting from some currency to dollars. Okay. So I have two implementations of this. I have this one, which is going to call a service at this fixer.io. Okay, so it implements the interface. I give it a code. It's going to give back a double. What does it do? Well, creates an HTTP client and then uses a method on HTTP client to get a string. So we're just making a call to this endpoint, right? Now, notice that when I say client dot, there's get string async, and there's a lot of methods here that all end with the word async. We're not really leveraging this right now, but we will here shortly. But I'm going to call this and just call result on it, because what getString does is it actually returns a task. Okay. Now, because it returns a task, this is something I can await on, which we're not doing yet, but we will do here in a bit. So right now what I'm doing is I'm just calling this method, it's getting me a task, and then I'm just calling result on it. So in other words, in effect, this is going to then get the string from this endpoint synchronously, okay? Because it gets a task, but then I immediately ask for result, so we're blocking right here until I can get it. And then it comes back as JSON, so we just need to get the rate out of there so that we can return it, okay? So then I have another implementation, and this does the exact same thing, it's just a different service. So this is openexchangerates.org. And so it creates HTTP client, it's going to, get rid of that exception for a second, it's going to make the call result, just like we talked about, and return it. Okay, so I have two services here that do the same thing by calling two different web services. And right now they're set up so that both of these work synchronously. Okay, so in my program, what I'll do is I'll just create an instance of the first one, I'll call getRate. I'll create an instance of the second one, I'll call getRate. So this is all going to happen synchronously. So that means that when I run this, what I should see is that it's going to call the first one, and then we wait, and then it calls the second one. Okay? So if it takes 2 seconds to call each service, it's going to take 4 seconds for me to get both of them, right? All right, so now I want to do this more in parallel. So what I'm going to do is I'm going to comment out this code, and I'm going to use this code. And so now what I'm doing here is I got a little list of services. So I could have a bunch of them, but right now I have 2 of them that implement this interface. So now I'm going to create some tasks. So I have a collection of tasks. The first task is to call the first service, getRate. The second task is to call the second service, getRate. Okay, so now I've got 2 tasks. And you notice I call task.run right here. So in other words, this task is going to immediately start running, and this task is going to start running. Now they're both off running, right? Then I call task.waitAny. The idea here is I just want to wait until one of them finishes. Don't care which one, just one of them. And I put a timeout in here, it's, 5 seconds. It's in milliseconds, right? So 5 seconds. Now, this integer here, this WR, when I call waitAny, okay, it's going to tell me first of all, it's going to block, and it's going to wait until one of them finishes. And then this is going to tell me the index, right, of which task completed. Okay, so when, say, the first task finishes, well, then this WR variable is going to be 0. Instead, if the second one finished, well, then this would be 1. Okay, it just tells me which task finished. So if none of them finished, because my timeout hit, for example, okay, then I get a -1 back. And that's in the documentation. You just look at the documentation for waitAny. And so this way I can say, if the wait result is -1, that means my timeout was hit, so write timeout. Else, it wasn't, so that means it completed. So let's print out some information about the rate that we got back. Okay, so let's get the result of the task, which will be that double. And then also I'm just printing out the type name of which one actually finished. Okay, so yeah, let's give this a quick run here. And so, yep, one finished, and it was the OER service. All right, cool. All right, so let's do a couple quick experiments here, which is, let me go to one of these, and let's slow it down, okay? Or, well, before we do that, let's give this a really, really short timeout. So maybe 2 milliseconds, because I just want to confirm that it's actually going to hit that. So you can see I got timeout, right? Because none of them came back in time. All right, let's put this back to 5 seconds, and let's show one other thing now, which is I'm going to go to one of my services, and I'm going to make this one take a really long time to execute, so I'm going to slow it down by giving it a sleep, and I'm going to print something out to the console in here. Because what I want to show is when I run this, even though one finishes, there it is, it finished. If I wait a few more seconds, the other one still finishes. In other words, when I call something like, I start up my tasks, and then I call waitAny, basically what I'm saying is, once one of them finishes, start running this code. But the other one still keeps going, right? I'm not canceling the other ones that are running, right? I just started executing code as soon as one of them finished. What I might want in this case is once one of them comes back, I want to tell all the other ones to basically stop, right? Because I'm not interested anymore. One of them already came back. Okay. Well, there's a way we can do that, but we're going to have to do a little bit of effort here. The other thing to keep our eye on is, if I look at one of my currency services, where is the actual long-running stuff happening, right? The high latency operation. Well, it's actually happening here, okay? So if I start wanting to do cancellation, I would want this getString async to be able to be canceled, okay? There's no point in me finding out if something got canceled and then canceling it down here somewhere, right? Because the long-running stuff is really already finished, okay? But I need a way to tell the system this thing needs to stop if it's in the middle of still going, okay? Okay, so that's cool. So a couple of things here. When tasks run in .NET, there are several different reasons why a task may finish. It may finish because it ran to completion and everything's fine. It may finish because it was canceled, or a task may actually finish because an exception was thrown, right? And so, and we already talked about that if an exception gets thrown in a task, it'll be thrown at you when you try to get the result or when you wait on it or do things like that, okay? But this is important to realize that just because a task finished doesn't mean you've got an answer. It could be finished because it was canceled or because there was an exception. Okay, just throw that out there because we're going to need that in a second. Now, this cancellation issue, tasks do support cancellation, and the way this is done in .NET is via something called a token. Basically, when you start up a task, you can give it some sort of token, and then it's up to the task to then check to see if a cancellation has been requested. In other words, task cancellation is sort of a cooperative thing because we don't know what that other task is doing. It could be doing some really, really critical stuff. It could be opening up files. It could be doing all sorts of things. And we don't want to just terminate it or abort it, right? We want to tell the task, hey, somebody's asked for cancellation. You should just stop whatever it is that you're doing. And then we leave it up to the code within the task to be looking for this cancellation. And if it sees it, then clean up some resources or do whatever it needs to do. So for example, if you have a task that's doing a loop of like 1,000 things, every time through the loop it should check, hey, has somebody asked for me to cancel? And if it's yes, then it should break out of that loop and not do any more. Okay, so that sort of thing. So here on this slide I have an example of I create this token source. That's something I can use to create tokens, so that when I create the task, I give the task the token. Okay, and so then I can start the task running, and then at some point later I can wait on it. But this also allows me to call source.cancel, and then that will signal, right, to all the people that have tokens that a cancellation has been requested. So on the other side, well, here, this is where I call like cancel. So I create the task, I give it this token, I start it running, and at some point later I decide to call cancel. So I call cancel on the token source. That sets the cancel flag, if you like, on all the tokens that have come from that source. So then inside of the task, so here's this do work. This is the code that's running in my task. It can basically check to see, right? Right now this is a big loop. It's just looping forever and ever and ever. But each time through the loop, it checks to see. This is one way to check, right? It says throw if cancellation requested. So if a cancellation has been requested, we're going to throw an exception. Instead, I could just ask the token if cancellation has been requested and then do other work. Okay, but the point here is tasks have to sort of cooperate in this, right? To check to see it needs access to the token. It's got to have a way to get it, right? In this case, it's being passed in, and then it's got to look at it to see what's happening. Okay, we're going to use this here in just a second. Now, one other cool feature, though, is that tasks can also be chained together with other tasks. So this is a kind of a cool way to do like a callback, which is you can start a task running, but then tell the task, hey, when you're finished, call this other task. This can be very useful for example, UI updates. So you start a task running in the background, and when it finishes, it's going to run another task which updates the UI back on the main UI thread. So just schedule a task to run once another task is finished. And in our case, in our web application, this is going to really help us out because we can start off our currency service calls and then tell each one of those, hey, when you finish, go call this other task, which will then generate a response on the web page or whatever it happens to be, right? And we'll see when we put this code in how this is going to be really useful, right? Okay, so the other thing you can do is when you do chain together a task, you can say, all right, well, when you run to completion, call this other task. When you're faulted, call this other task. And if you're canceled, call this other task, right? So when you create your task, you can set up all these different things for it to do. So if you've ever done any JavaScript and you've written some Ajax and you've set up those callbacks with, if it's success, run this JavaScript code. If it's a failure, run this other code. If it's something else, run this other code. Similar thing, right? But it's kind of a cleaner way to do things with these continuations rather than what gets involved. We try to do callbacks and things. So I have another example here, another little demo. So I'm going to come over here and we'll open up demo number 4. All right, this is our last console application. And so what we're doing in demo number 4 here is we're starting to try to set this up in a way where we can start handling things like cancellation and errors. So we still got our services. Our services now, though, we are still do the exact same thing, but now each one of these services takes a cancellation token. Okay. So when I build my little definition of my currency service, you pass me a currency code, I'll give you back the rate. Oh, but you can also pass me a cancellation token. And then what each service promises to do is it's going to check that token, right? And if it's canceled, then it'll do something with it. All right. And the same with sort of the other one here. Okay. It'll look at that token and then do something with it. All right. But this is not ideal because really it's this operation here where we're actually making the web service call. How do I get that to cancel? Because that's where the work is really being spent. But this is kind of our first attempt, right? So we modify these to take a token. We come over here to our program. Now we have this written a little differently. We've got our collection of services. We create our cancellation token source. We loop through each service and we create a task from each service. So here's a task to call get rate on the first one and then give it a token from that token source. And then for the second one, the third one, however many we have. But for each one of these, we specify a continuation here, which says when you're continue and then only when run to completion. So if I'm running all these tasks, I start them all running, and for each one of them, when it finishes, it's supposed to call this process result down here, which will print out the result. Okay. So if one task finishes, and everything's fine, it'll call process result. If the other task finishes, but it finishes with an error, it will not call process result. Okay. See, this is a problem I had with the first example, which I didn't really show, which is if I call wait any, the first one that finishes could finish because it had an error. And then I'm sort of stuck because, well, one finished, but it erred. How do I get to the second one? That's sort of difficult. Here, each task is sort of its own little thing, right? And whenever one finishes, it calls process result. Okay, so I've got one here that does what it does, and it does it really slowly. And I have the other one that does what it does, but maybe throws an exception or something, right? So I've got one that's slow and one that sort of blows up. And so I can run this, and now I'm waiting. One blows up, but doesn't do anything because it doesn't have any sort of continuation to run in that case. But then the other one finished, and it ran its continuation, and then it called process result, which printed out the concurrency rate here. Okay. So it's getting better. Now I've got it set up in a way where both can start off running, and when one finishes, it does something, and when the other one finishes, it also does something, but if one finishes with an error, then it won't do that, right? So let's get rid of this throw exception. Now we can maybe let both of them finish. So one's kind of fast, there it is, and then the other one takes like 5 seconds because we slowed that one down, and then it finishes. All right, cool. A little better, a little nicer. Still not ideal though, because really what we'd like to have is when one finishes successfully, we'd like to make sure and cancel the other ones. Okay. Oh, and by the way, we also haven't handled this issue of scalability. In other words, if this was in a web application, we still have a thread that's just sitting around waiting, that's blocking on result here. In other words, I have my main thread. I fire up 2 tasks. Those 2 tasks are running each in their own thread pool thread. But task 1 is sitting here blocking that thread pool thread until the result comes back. The other one blocks until it comes back. So in other words, while I'm waiting for the responses to come back, I'm monopolizing 3 threads. that are just waiting, right? I've got my main thread that fired off these tasks and these two tasks. My main thread is it can be allowed to sort of complete, but it's got to wait for these guys to finish. And so then these guys each have their own threads that are running. So we can do better. And we also want to move this into a web application. Okay. So a lot of the .NET APIs that do I/O stuff, like networking, files, whatever, have async versions now. And so I showed this earlier, you know, read file async, read string async. And anytime you see a function in the APIs that ends with the word async, that's just a convention that Microsoft uses. Any function that ends with async returns to you a task. And because it returns to you a task, you can do everything that you can do with tasks. You can wait on them, you can call wait any on them, you can do all that task stuff. And so those are the ones we want to use to support this. Now, what's really nice, though, is if you look at some of these functions in the API that are async, like getString async here, and you look at what parameters it takes, there's overloads. And a lot of times what these will do is there'll be one that can take a cancellation token, right, potentially, so for cancellation reasons, okay? Also, to improve scalability in our web app, we'd like to be able to release this thread while the waiting is happening and then sort of resume once it finishes. And so in C#, this was the real purpose for async and await. And when async and await were introduced in C#, it was to make it easier for us to do sort of this callback type setup, right, to have continuations, but have it read like synchronous sequential code. Okay, so here I have a button click handler in the slide. And so it's an event handler, but I mark this event handler as async. What that allows me to do is then somewhere inside the function, I can now await on something. So PyResult here is a task. So in other words, okay, you call the button click gets called. I create a task. Here's my task. I can now await on this task. When I await on this task, sort of something that returns something is a task or something that returns a task, what can happen is the main thread can be allowed to be released and do other things, okay? And then once this task completes, code can resume here, right? And can run everything that comes after the await. So you can think of like the code before the await and the code after the await. And so the code after the await is sort of like a callback. This is the code I want executed once the awaited thing finishes. But I can just write it as just one single function here, like it's synchronous, right? I will talk a little bit about how that happens. But the best thing to do is just look at our final example, which I'm going to pull all this together, and I'm going to open up demo number 5. And demo number 5 is an ASP.NET Core web application. So this is where we start pulling all these different features together to really do something useful. And so what I've got in my ASP.NET Core web app here is I have my currency service, but now I've changed my currency service to be task-based. You call getRate and give me a cancellation token, and I'll return not a double, but a task of double, because I want you to be able to await on this. Okay. So now what does that mean for the implementations? Well, if I look at my first currency service here, all I'm doing now is this getRate function returns task of double, and I mark this as async. Okay. Now inside the function, because this is async now, I can await on things. So here I'm creating my HTTP client, and I await on my getAsync call, and I can pass it a token. So I'm not using getString anymore. I'm using getAsync, and so this method is going to return some sort of response message. Okay, but it returns a task. And it takes a cancellation token. Oh, so I can sort of pass this token through to this asynchronous function. So if I cancel on this, this getAsync function is looking for that, and it'll see it and it'll be able to cancel itself. And because I'm awaiting on this, when this getRate function gets called, the code will run up to here. It'll make this call on a separate thread pool thread as a task, right? The thread will be allowed to be released to go do other things. And then when this finishes, a thread pool thread will be obtained so they can run the remainder of this code. Same thing with the OER service, right? I set it up to return a task, it's async. I await on this call, right? I can even await on where I parse the JSON or something. So now, in my home controller, I have an action here called currency rate. And so I get my list of services. I create a task for each one of those. What does each task do? It calls get rate, passes along a cancellation token here. I can specify a timeout on the cancellation token. Okay. And then what I'm going to end up doing is I'm going to wait. I'm going to call wait any. I'm going to go back to using wait any again. So I wait any on these tasks. So now I've got two tasks running. They're calling the web service at the same time. I'm waiting for one of them to finish. And then when one of them finishes, I say, well, why did it finish? Did it finish because it was successful? Oh, yes, it was. Well, then get the result and then cancel the others. So I call cancel on the token source. Okay. Boom. And so then I just break out of this loop and then I print out the currency rate to the web page. On the other hand, I could be running this. So all the tasks are running. Let's wait for one of them to finish. Oh, one of them finished. Did it complete successfully? No. Oh, well then remove that one from the list because that one blew up or something bad happened with that one. So forget that, okay? And then call wait any again, okay? So give me another one that's finished. That one's not, that one's out of the list now. So now just give me another one that's finished. I don't care which one. Oh, here's this other one's finished. It completed successfully? Yes. All right, get the result and cancel any of the other ones that we have running. So we could just very easily extend this to 5, 10, 15 services, however many we want, right? So if I was to run this, let's get this up and going here. We're building. There we go. All right, so I'm going to make a request to my web application. And so to do that, I'm going to go to home/currency rate, and I get a currency rate. So one of them came back at 1. But now what I'm really interested in is I need to try some experiments here. The first thing I'm going to do is let's specify a really short timeout. So there's no way they're going to have a chance to give me a result in time. Let's make sure we cover that scenario. Yep, unable to get data. Looks good. Okay, let's check another scenario. Let's put that timeout back to be something really long, and let's go into one of our services, and let's have this service throw an exception. So one of them blows up and one of them doesn't. So what I'm expecting to have happen here is I should get a currency rate, and I shouldn't get any sort of error or blow up or anything, because yeah, the other one blew up, but that's okay. I just sort of dealt with that and said, no, let's try the next one. And it may be slower if it's the slow one that comes back this time, but I should get a rate. Whoop, I got to make a home currency rate. Yep, worked. All right, let's try one more experiment. Which happens if this one throws an exception and my other one also throws an exception? So now all the services that I have are all going to throw errors. All right, so none of them are going to work successfully. And so we should just get that we were unable to get it. And of course, I could give the user a better message or something like that, but unable to get data. Oh, cool. All right, so it looks like it's working good. And just for one more thing I could check, which is if I was to make these so that they both work, but I'm going to put maybe a well, yeah, I mean, you could try this with the demo on your own, but basically just to confirm that when one of them finishes, the other one actually does get canceled, right? So we're not wasting work there. But what happens now, just to review real quick here, I know we're got to the end of our time, but when this action gets called, there's going to be a thread that starts running this action. So ASP.NET gets a thread from the thread pool. That thread starts running this action. It gets down to here where I call, so I start off these tasks. Okay, so these tasks are now running on thread pool threads. Okay, when it gets to this await when any, okay, that means that this thread here that's running this action can be released to go process other requests. Meanwhile, these other two tasks that are running to get these currency services, in each one of these tasks, they get to hear where they await on this async call to get this result back from the HTTP client. And again, when this happens, this thread can be released, right, to go do other things until we get a result back. So in other words, a user made a request to my website. I start running some code. I go off to call some web services to get some currency. I fire off 2 tasks. I'm waiting for both those tasks to complete. I'm not using any threads. This request is not using any threads from the pool while those HTTP requests are sort of in flight. And so now all 3 of those threads can go process other requests. And I've got people that are, clicking places in my website or viewing the about page or doing whatever, and I keep my site really nice and scalable, right? Now, one of those web services finishes. And so then a thread pool thread is going to be obtained to run the remainder of this code, which is going to parse the JSON and get the result and return it out, which is going to then signal an object so that another thread pool thread can be obtained to then run the rest of this controller action, right? So the bottom line here is my ASP.NET web app is only using threads to do work when work needs to be done. If all I'm doing is waiting, I'm not monopolizing a thread pool thread to do that waiting. And the more thread pool threads I can free up, the more requests I can handle simultaneously, right, without having to create new threads. And so it makes my web application much more scalable because I'm doing that waiting in a much more efficient way, right? And then I can handle things like cancellation by being able to pass this token down into my tasks, and I can handle errors that occur and things like that just by being a little bit smart about how I use things like wait any or when all. Now, this async and await stuff, I just want to show one more thing just with the time I have here. If you were to actually go look at our code, so this is the web application that we built here, and so here's my DLL, and I'm going to go browse this with .NET Reflector because what I'm interested in is looking at what this async business gets turned into. And so here's my controller, and here's my currency rate action. And one of the things that I will notice in here is that when my currency rate action is running, it's actually creating an instance of an object, this currency rate D__4 thing, and calling its constructor, right? And the same thing with if I look in my, here's my currency services. So if I look at one of my currency services, like the OER service here, and my get rate, the same thing. I see it creating an instance of an object. Here's the object right here, this little get rate object that has a constructor and a bunch of methods like move next and whatever, because what the system does is when I've got some place where I do an await, it basically takes this function and turns it into a class, turns it into an object. And you can think of all the code before the await is in one function of that object, and all the code after the await is in another function of that object. And so that's how a thread can run part of it because it calls the first function. That thread's released, and when that work finishes, it grabs a thread and then calls that other function, which is the part after the await. So it turns it into basically a state machine, basically a little object that has the, sort of the code that does the work, and then the code that's kind of like the callback, without us having to actually break this out into its own function to act as a callback, right? And so, yeah, it's a nice example here, just trying to use tasks with async await to do something, not totally trivial, right? Call these 2 web services in parallel and then work with the results that we get back. Cool. All right, so like I said, you will have that code available at the URL that I put into the chat there for all 5 of those demos that I did. You can sort of play with them, and I would encourage you to sort of do experiments, try to break them in interesting ways and see what happens, and have some fun with that. Okay. If you also receive an email with a request for you to provide an evaluation for this webinar, I would really appreciate it if you could do that, because that helps us to make sort of these better in the future, and can also see what we can fix and things like that. And I mentioned that there'll also be a way to view a recording of this, so when you get that email, there'll either be information in there, or you can ask too about where that'll be available, but that will be available later as well. Okay, so we went a little over time by about 5 minutes, but I'm happy to sort of stick around for a little while if anybody's got questions, and I can sort of do my best to see what we can answer for questions. So I'm going to take a look over here and look at the questions panel. So, okay, so one question, I'm going to try to go from the top down here and see what we got. It says, I want 90% of my code to utilize all cores of the processor. So that's really when we get into sort of using some of the task parallel stuff that I mentioned. And so we didn't get into that too much in the webinar, but what I would tell you to look at are functions like parallel dot for each, right, or parallel dot invoke. Okay, this allows you to have a collection of tasks and basically say that you want all those tasks to be run in parallel. And what will happen is it'll automatically create queues for each one of the virtual cores that you have on your machine, and then run that work in parallel. Now, when it comes to how do you assemble the results from this happening, like you've got a list of 1,000 items, and so you spread that out across 4 cores, so each core gets 250 to work on. How do you then assemble the results from all this? That can get a little involved depending what you're doing, but we have some thread-safe collection classes, so things like concurrent stack and concurrent queue and concurrent bag that are collections that you can add stuff to from multiple threads, from multiple tasks simultaneously, and it'll do it in a thread-safe way. So you don't end up with sort of issues with that, okay? Because you're introducing shared state in that case, okay? What do we got? Let's see what else. Whether continue with will switch to UI thread. So when we mentioned continue with earlier, continue with on its own will not execute on the UI thread. And so to get something back executing on the UI thread, typically what you'll do is in your task, you can specify a continue with, but when you specify the task that it's going to continue with, you have to tell that task to use a different scheduler. So you tell it to use the synchronization context scheduler, and then that'll cause that task to run on the main thread. It doesn't happen just by default, but you have to make sure that you specify that when you specify the task to be used as the continue with, right? And I kind of showed that briefly earlier. When you create the task, and then when you start the task, you can specify sort of which scheduler to use, so you have to actually do that, okay? Hey, a better name would be get rate async as per Microsoft convention. So yeah, what that individual is saying is when we did our interface over here for our currency service, that when we change this to be from double to task of double, we should have named this get rate async instead of just leaving it as get rate. Yes, I would agree with that. That would be nice, because then it would follow the same convention as what we see in the frameworks. So if somebody is using my currency service and they see that the method is called getRateAsync, it's sort of a tip to them, make it very easy for them to see, oh, this is getRateAsync, this returns a task, this means I can wait on this or do other things with it, and it just helps for readability, right? Not necessary, but yeah, probably a good idea. Let's see what else we got here for questions. Hold on one second. Let me make this bigger so I can see. Could you add a simple example for us to download that runs 2 or 3 tasks simultaneously, but waits for all 2 or 3 to finish before continuing, looking at how to run tasks concurrently, but pass all data back to the main thread. So yeah, we could extend this to do that. Basically, in here, for example, where I'm doing wait any, we also have, of course, wait all, which would wait for all of them to finish, and then you can use a combination of those. So you could have one collection of tasks which you need all of them to finish, and another collection of tasks which you only need 1 to finish, and then both of those could be wrapped in another task where you wait for both of those to finish. So in other words, you could have a parent task with 2 children, right? One child is made up of 5 tasks where you need all of them to finish, and another one is made up of 3 tasks where you only need 1 to finish. And so your parent task is basically saying, I need to wait until all of those are done and one of those is done. And so you can sort of compose them in that way and sort of play around with that, right? And then when it comes to, you can combine this with demo 4, where we use the continue with as far as what's going to happen when these finish, instead of doing it this way, and sort of, you know, do your combination. You can usually get to work, okay? Does it make sense to use configure await false for ASP.NET Core web apps? Popular question. Answer is no, okay? And that is actually a really, really good one, so I do want to take 1 second on that one. Because configure await false is a really popular question that comes up all the time. So if you actually give me 1 second, it's going to really help if I just bring up another quick slide that I have. So just if you can just give me 1 second, I can see if I can do that. Okay. Okay, so give me 1 second. Okay, so configure await false. This is all about synchronization contexts and sort of what will happen. There's a little piece of code here. This is a WPF application. And I've got a method that says when it's activated, I'm going to go off and run something, and I'm going to wait and get on the result of this call to some web service or something like this, right? And there's a possibility for introducing sort of deadlock in here because the GUI thread waits for the thread to finish because in this get result. And it can't because the GUI thread, you know, we get like a deadlock sort of scenario. And so you notice that this red block on the slide says you must apply configure await false to every task you await on. So here I've got await, HTTP client, get string async, and then configure await false. So in other words, do not use the calling synchronization context for improving performance. Okay. The thing is, when we're talking about something like an ASP.NET Core web application, there is no synchronization context because there is no threading model as far as updating the UI from a thread, from a background thread. And so doing this configure await false when we do an await on something is not necessary in a web application. But where this is really important is if you're writing a class library and you don't know where people are going to be using your class library. So inside your class library, you're awaiting on things, okay? But you don't know how people are using your class library. They could be using it in a web application. They could be using it in a Windows application. They could be using it all over the place. And so it's important to basically use this when you've got, you know, library code that you don't know how it's going to be used. It's going to be used in the context of a GUI app or the context of a web app. And so you want to make sure that you don't introduce some sort of issue in their application. If you're creating a class library and you don't know where that code's going to be used. I would recommend that you do just a quick Google search on this, on configure await, read a couple articles, and sort of, you know, learn more about what's going on there, especially if you're going to create asynchronous concurrent code in libraries that are going to be used by other people. Okay? What else? Let's see if we can, I'm trying to go down the list here because we don't have a time to get to everything, unfortunately. C# has a class of delegate. With that, no need to implement a task. Let me just get down to where that is. Any pros and cons compared to using async and await? So what this person was talking about is since very early on in .NET, we've had what's called asynchronous delegates. And so what you can do is create a delegate and you can call begin invoke, and then you have the ability to call end invoke on that to get the result at some point later. So you can basically do like callbacks with delegates. And the question is there any advantage to using that system versus like async and await? No, they're basically really the same, okay, as far as what's happening. It's just that async and await was really just introduced to make doing callbacks easier from a readability point of view. That you can write the method, it looks synchronous, you read it like it's synchronous, but there's really this, it's being split like that with callbacks. If you do set up a delegate and you use that with begin invoke and end invoke, you'll end up with the same benefit at the end of the day. It's just, it makes the code a little bit harder to read, a little bit harder to follow, a little more confusing potentially. but under the covers, the same thing is happening, which is asynchronous delegates are still built on top of thread pool threads. They actually use queue user work item under the covers, and tasks do the same thing. Now, tasks do provide a few more features in the way that you can use them with like when any and wait all and cancellation and things. They're just a little bit cleaner, and so there's less code that you maybe have to write. But performance-wise, as far as actually executing the work, they'll be the same. Can you please repeat your explanation? How does MVC controller schedule its actions execution? All right, so just briefly on that one. When a request comes into an ASP.NET web application, there's a worker process that's running, right? So if we're in IIS, it's W3, WPEXE, it's the worker process for our application. In ASP.NET Core, it's a little different in that we have Kestrel that we can use that we usually reverse proxy in front of. But anyway, there's a process that's there for our application. And when a request comes in, what ASP.NET Core does, it obtains a thread from the pool. Okay, and the thread pool is basically has different limits set on it. For ASP.NET Web Apps, it's much higher numbers as far as how many threads are available via the pool. So a request comes in, a thread is obtained from the pool. That thread is used to execute our controller action. Okay, I mean it's that thread is for that request. So it's going to go through the routing system. It's going to do all the work, but then that thread is going to end up running this action. Okay, and so now that thread cannot be used for processing other requests until this action finishes. Right. Now, in a traditional application where everything's synchronous, the thread runs our action to completion, it generates a response, the response goes back. Once the response goes back, that thread is returned to the pool. It can now be available to be used for other requests. If during the execution of this action, we end up awaiting on something, okay, and then that, in this case, ends up awaiting on something that uses one of the APIs in the framework that return tasks that use something like IO completion ports or KQ on Linux or whatever, then these threads can be allowed to be released again and do other things. So this thread that was running this action can actually be returned to the pool to handle some other request that does something simple, right? And then when this thing finishes, and we're going to resume here, run the second half of the await, in other words, ASP.NET can go back to the pool, get a thread to be able to finish out this action and return the response. So in other words, it doesn't look any different to the end user. The person in the browser, it still takes just as long in the browser, right? In other words, they make the request, they're waiting. They see a response from the server. It takes the same amount of time. It's just on the server, we can let those threads go do other things while we're waiting to keep our server more scalable. If we want a response, if we want an experience on the client where the user sees some message or something that says working, and we make it asynchronous on the client, well, we've got to do that on the client. We've got to do some AJAX or something. So that on the client, they click a button, we make an AJAX call to this currency service, and then when this currency service finally generates a response, it goes back to the client, and the client gets it via the AJAX call, and we can update the page. Right? But you may have to combine them depending on the user experience you have. But whether you do this async here or not, doesn't change what it looks like to the client. Okay, it just can potentially keep our web app more scalable. All right. Let's see. The cost of development when integrating with non-task aware code seems expensive. For a site that has a low access rate, are there any drawbacks to always coding with tasks? Absolutely. I would never use tasks unless I have discovered there's a justification to do it. Okay. When I'm creating my own ASP.NET web apps today, all my actions and all of my controllers are all just regular actions, synchronous, no problem. When I'm doing stuff like accessing entity databases with Entity Framework, I'm probably just doing it synchronous, right? Because it's in the context of a web call. I'm not expecting to handle hundreds of thousands of requests or something. I'm not concerned with that sort of scalability issue. I don't expect super high latency to my database. It's not worth it for me to go through all the work to do these things asynchronous, set these things up to be task-based, and do all of that. I've had applications where I've been doing some stuff with Entity Framework. I've switched things to be asynchronous to use tasks, and it's actually made the overall application slower because of the overhead that's involved with doing things with tasks. Maybe it made my app a little more scalable, but at the cost of slowing things down a little bit for everybody. So in this example where I'm calling these web services, because there are these free web services that are out there, I expect them to sometimes be really slow and really unreliable, and I don't want to impact the overall scalability of my app just because of these really bad services. But I still want to use them because they're free. And so in this case, I've decided, hey, it's worth it for me to go through the effort here of making this an asynchronous controller action and using tasks so that I can sort of wait on these as efficiently as possible for the rest of my app. But yeah, I'm not going to overcomplicate my life and make everything asynchronous and task-based unless I have a really good reason to do that. Okay, keep it simple, right? Because then I start introducing other issues with thread safety and stuff, depending on what I'm doing. Okay. Let's see. In a cancelable, should a token be checked after every code block to cancel the task? Yeah, when you're inside your, like in my get currency rate here, let's go to one of my services. I'm getting a token. How often I look at that token, right, and check that token is totally depends on what I'm doing inside the method. So you can see I've got is cancellation requested or can be canceled and throw if cancellation requested and other things available in here. So how often I'm looking to see if cancellation has been requested, it depends what I'm doing in here. In our currency example right here, the only place it's actually being checked is I'm passing that token through to this getAsync call so that getAsync can be looking at it. Okay, and that's internal to the framework of how it actually does that, right? Because I want to cancel that long-running work. But I may want to check it before I do the parse. I may want to check it after I do the parse. I don't know. Okay, it just depends on what it's doing. If this method needs to call 10 services, yeah, I'm going to check the token after each call, right? Call the first one, check the token. Call the second one, check the token. Call the third one, check the token, so I can, stop. It's just going to depend on sort of what I'm doing inside of here. But yeah, the more often I can check it, the more efficient I can make things, right? So I can cancel as early as possible. But sometimes you're doing some big expensive operation in here where there's no way to cancel it in progress. Just depends. Yeah. I thought configure await was done away with in .NET Core. Not done away with, it's just you don't need to use it. Because .NET Core right now, we can only create console apps and web apps. And in those scenarios, we don't need it, okay? However, you can create a .NET standard library that could be used in Core, but could also be used in full framework apps. So if I'm creating a .NET standard class library and I'm doing some asynchronous stuff in there and I'm waiting on it, again, I don't know if somebody's using that class library in a ASP.NET Core app or they're using that class library in a full framework WPF app. So it's still something I need to think about if I'm creating a .NET standard library that could be used in both places. Okay, but if all I'm doing is just core stuff, all core stuff, top to bottom, front to back, I don't need to worry about configure await at all. Yeah. Let's see if maybe we can get one more, maybe or so. Okay, so one question in web development, we have to wait for the thread to finish without the page. Otherwise, so the page will be loaded, and how do we push the result to the user when the view finishes? Yeah, that's important, right? When we talked about that, which is if I write my concurrent code in this action in such a way that all I do is just fire off a task and then I let this action finish, I have a problem because it's going to generate the result, and the result's going to go back to the client before the task finishes. So when the task does finish, there's nobody listening for the result, right? So when I use await here, remember, code is not allowed to progress past here. This code does not run, but it also doesn't block the thread, okay? The thread's allowed to be released, and then this code resumes, but the result that I send to the client is not sent to the client until all this work is finished, right? Because the result will not be sent until this code executes. This code won't execute until whatever I'm awaiting on finishes, and then this code's allowed to run. So that's why I said it doesn't look any different from the browser. It still takes just the same amount of time, whether this is asynchronous or not, okay? If I want to make it asynchronous on the client, that's where I have to make one call via Ajax and make another call, or look into something like SignalR, WebSockets, something like that, where I can push a change notification down to the client when it happens. But that's sort of a different model, right? Here, we're not trying to accept the call, generate the response, and then push a result down. we're trying to make our service a little more scalable, be more efficient with how we use threads. Okay. Can you tell us why async void is bad? This might tie into awaitable delegates. Yeah. You should never have an async function that returns void. The only time you have an async function that returns void is in the case of event handler. The only reason why this is actually permitted is for event handlers. And so to make event handlers work in places like WPF, if you want to have async event handlers, you need to be able to do async void. But there are reasons why that's a bad idea. I don't really have the time here to go that, but there are some good articles and resources out there. If you just do a search on something like, C# async void. And here's an article on MSDN about best practices in asynchronous programming. And this will talk a little bit about sort of avoid async void, prefer async task methods over async void methods. So in other words, something like this, right? Versus something like, this. Okay. But I'll leave that for you. Let's see. I think that might be it. Let me just take a quick look. Last one. Please explain the difference between task wait any and task when any. Wait any is waiting, basically blocking, waiting for the task to finish, and then when one of them finishes. So I think we had a wait any. Let me go back here and we can see the difference between the two. Let me see. Let me open demo 4. Was it this one? Nope, it was 3. It's just a little bit different model as far as the code that you're writing. So here I have a wait any. If I look at the parameter list for wait any, one of them takes an array of tasks. Actually, I think all of them take an array of tasks. Yeah, wait any takes an array of tasks. So you give it an array of tasks. You can give it a timeout and some other things. But then that'll wait until that task finishes, so it'll block. And when it completes, the return type of wait any is an int, which is what is the index in that array of the task that finished. Okay. On the other hand, when any, which is the one we did in our last demo, just had a different sort of signature to it, right? So if I look at when any, hopefully I can get my IntelliSense to work for me. Oh, I gotta wait for my NuGet package restore to finish. There we go. So this is just a little bit different signature. So this doesn't return an integer. This returns a task. Okay. So task when any. So task wait any return an integer of which task finished. Task when any returns a task of the task that finished. So that I can await on, because since when any returns a task, I can await on it, okay, and then be able to get the result of that task, okay. Where wait any, I cannot await on that, because wait any just blocks and waits until one of them finishes and gives me the index of the one that finished, right? So because I'm awaiting on when any, this allows this thread to be released to do other things, where with wait any, that thread is just blocked until one of them finishes, and then I get the index of which one finished. Okay, but I can't let that thread go to go do other things. Okay, cool. Oh, I can't resist. I gotta look. See, a couple more just popped in here. Okay, so just 2 really quick ones. In the case of nested awaited functions, does control flow all the way up the call stack? I think I sort of know what you're saying there, and the answer kind of is yes, which is when I start running my action, which is in home controller, and it starts running this, and I get to my await here, okay, it's awaiting on this thread's gone, it gets released, and then these other ones are running, each one of those await, like I said before, and then When I'm awaiting in these threads get released, and then once one of this, the IO completion port that's used here to get the response back triggers, then a thread pool thread is obtained to run the rest of this code. This returns this, which causes this thread to finish, which is going to then signal this so that this can finish. And so in order, in an ASP.NET web app, to make sure that you're really getting the scalability benefit that you think you're getting, it's got to be sort of async all the way down, right? Which is, in order for this asynchronous controller action to have benefit, it's got to be awaiting on something that is also asynchronous, that awaits on something, and then eventually we get far enough down the stack, we get to the point where we're calling a system API call, right, that's able to use operating system functions like completion ports and kernel object signals and things like that that allow the waiting to be done efficiently. Okay. And somebody asked about the sample codes and the video recordings. Yep, when you get the in the GitHub, you'll have the code and everything in there, all the demos, and then you'll get that email that you'll get. Well, they'll have the eval instructions, and then it'll also have the instructions on how you could potentially watch a video later. The videos will be posted to the Wintellect website so that they are viewable at a later time. Okay, we've gone way over. It's like 30 minutes, so we got to go ahead and wrap it up there. Thanks to everybody for attending. Hope you got at least a little something out of that. And then, you know, feel free to, again, I would encourage you, use this code. Maybe not use it in your production stuff, but use it as a learning tool, experiment, try some other things, and then look for a couple places in your applications where you can sprinkle in a little bit of concurrency, a little bit of async and await, just to get some benefit where you need the benefit. But don't make the mistake of some people of just going crazy and putting async everywhere and overusing it, because you don't want to make your code more complex and start taking on some of this extra machinery if you don't have a place where you can actually get benefit from it. Okay? Okay, everybody. Thanks, and have a good day.